Hey everyone, my name is Dr. Mary Van Vliet, and this is going to be the first of many lecture videos that you're going to get over the course of the semester for our Physical Chemistry 2 class. So today's lecture is going to be partly a mathematical review of concepts that I expect you to already know from your previous math courses here at Spelman College, and in part we're going to introduce some new formalisms or some new formulas to talk about mathematical concepts that you learned about previously. And so today's mini lecture is going to be on probability and expectation values. My hope by the end of this lecture video is that you will be able to calculate statistical quantities of interest. Some of the names that you might be familiar with: average, median, mode, variance, and standard deviation. But rather than doing that using some of the traditional formulas that you learned about in your algebra course, instead this time we're going to use concepts of probabilities or probability density, depending on whether we're talking about discrete variables or continuous variables. So some of that terminology may be new. Let's dive right in. All right, so let's do a bit of a review on probabilities and averages. And I'm going to set this problem up for you and then give you a minute to pause the video so that you can try and tackle these problems on your own using your previous knowledge coming into this course. So for this problem, we're going to imagine a room that has 7 people in it, and each person has a different age in the room. We've got one person who's age 15, 2 people that are age 17, one person age 20, 2 people age 23, and one last person age 25. And so go ahead and try and answer on your own the following 3 questions. 1, if you selected an individual at random, what's the probability that their age will be 23? 2, what's the most common age of people in the room? And 3, what's the average age of people in this room? So go ahead and pause the video, and when we come back, we'll go over the answers to this question. All right, so starting to think about the first question, when we're talking about probabilities, we're basically talking about what's the fraction of ages in this case that are our desired outcome divided by the total number of possible outcomes. So in this case, we're looking for an individual that's age 23, and there's 2 people that fit this description. And so what we would expect to see is that the probability of observing someone at a particular age, so in terms of my notation, this capital P here is going to stand for probability, and X is going to be sort of our independent variable, and it's going to denote what age there is. So X in this case could equal 15, it could equal 20, but X is going to be our age. And that probability is going to be given by the total number of individuals that meet that description. So that's where I'm going to call this N of X, or if you like, N where X is equal to 23, divided by the total number of people that are in the room. So you'll see this sometimes just given as capital N, or maybe you'll see someone write N tote at the bottom in order to give this a formula. And so this formula is a generic formula for probability. It's going to be very useful for us. And in our particular situation, we have 2 out of our total 7 individuals that have that particular age. And so it appears that in this case, our probability that someone is age 23 is 2/7. And the next question that we're asked is, what about the most common age for people in the room? This is a keyword in our case, most common being a keyword for mode. And the mode of its statistical distribution is, in this case, can have multiple answers. In this case, either 17 or 23. I really should say both 17 and 23 are our 2 modes for this distribution. And we can primarily tell that just by looking at the data and seeing that there's, 2 people that are these varying ages. But if you wanted to put this in terms of more mathematical language, we could say that the mode is defined as whatever this like the maximum of our probability distribution. So that wasn't too bad. And now let's talk about averages. And to transition us from thinking about averages in terms of how you learn them in your algebra class versus how we're going to start talking about them in quantum chemistry, I'm going to solve this problem two different ways. So here's one way that is probably what you're mostly used to from your algebra classes. We say that the average is the sum of all the possibilities. I'm going to use a little bit of shorthand to remember that there's 2 people age 17, so we're going to have to multiply by 2. Plus 20, 2 people age 23, plus 1 person age 25. And we'll divide that whole quantity by the total number of individuals that we have in the room. And in that case, that is going to give us, if we plug this into our calculator, that's going to give us an average of 20. Now, if I can mathematically rearrange this for us and introduce a little bit of notation that we're going to expect to see for the rest of the semester, one thing that is common in quantum chemistry is to denote this average using angle brackets. And so start getting used to seeing, in this case, because we're talking about the average age and x was the variable that we used to denote age, I'm going to put little brackets around this and say that this is our notation for talking about an average. But instead of calling it an average, we're going to call it an expectation value. So x is defined as the expectation value. And this angle bracket notation is called the expectation value. And because x is inside of the brackets in this case, we would say that this is the expectation value of x, the expected age of people in the room. And one way that we can see how to calculate expectation value is using a new formula that I'm going to introduce in a second. And to give you some motivation for that formula, let me go ahead and rearrange the math that I did just up above. So I'm going to go ahead and throw in a couple of the numbers that we had by default in this expression. And now what I'm going to do is, instead of adding up all the numbers and then dividing by 7, I'm going to say that what we're really doing is 1/7 times 15 plus 2/7 times 17 plus 1/7 times 20 plus 2/7 times 23 plus 1/7 times 25. So I haven't really done anything other than to take out this common factor of 7 or 1/7 and apply it to each of these variables. What I want you to notice is that based on how we defined the probabilities up above, each of these prefactors is the probability. And then each of these second numbers is whatever that particular age is. And so at least in this case, for these averages, we could say that our value for x takes on the formula that we're going to sum over all possible values of x. So I'm going to put x underneath the summation sign. And in this case, if I multiply together all of the probabilities times x, then that is going to give me my average as well. And so for a problem like this, where there's a small number of people in the room and you're given each of their ages specifically, it's probably easiest to use your traditional algebra method for coming up with this average. But for most of the problems that we tackle in quantum chemistry, where you are probably going to be given the probabilities rather than given the numbers of each distribution, this second formula, our way of thinking about things, is going to be most useful for us. And so let me go ahead and put a box around it since it's going to be so useful for us. Again, what we need to do in order to calculate the average using this formula is we need to know what the probability is for, in this case, seeing a person of each age, and then we need to multiply that by the quantity of interest. So it's not a surprise that what we found inside of the brackets was x, and what we put next to the probabilities was also x. In fact, there is a generalization of this formula which says that if I am interested in anything that is a function of x, it's going to follow the same formula where I'm just going to replace x with f of x. And so we can say that for this function more generally, the expectation value of some function of x is equal to a sum over all possible values of x, where we're going to multiply together the probability of observing that particular value of x times whatever the value of the function is. And so if for some reason we wanted to calculate what is the average value of somebody's age squared in the room, then we could do that, and we would just substitute, in this case, f of x would be x squared. And so for each of our possible ages, we would multiply the probability of seeing that age, which hasn't changed, times x squared, where x squared is a particular age. And so this formula, I would say, is going to be even more useful for us because it's not necessarily always just x's average value that we're interested in, but we want to know what that average value is regardless of whatever the function is. So now that we've done a little bit of review of that, how we calculate averages, how we will calculate averages in PChem 2, let's do a practice example. And so for this practice example, we have some kind of crazy mathematician gambler that's come up to us, and they are going to offer to play a game with us. So here are the rules of the game. A man is going to draw a card from a standard 52 card deck at random. And what I will tell you for this game is this person is an honest person, so it's going to be a truly random distribution. And if he draws an ace, you win $10. If he doesn't draw an ace, you lose $1. You owe him $1. And you can play as many rounds of this game as you like, and the rules are going to be the same for each round of the game. And so once again, I'm going to have you pause the video and ponder this question for a couple minutes. Should you play this game, and why or why not? And is there a strategy of how you should play this game if you think that you should play this game? And so go ahead and pause the video, and I would encourage you first to think about this question from your gut. So using your prior background knowledge or just your sense of whether or not this is a good game to play. Try and answer the question that way. And then secondly, try and see if you can apply this formula that I have shown boxed on the screen in order to answer the same question more mathematically. So go ahead and pause the video, and when we come back, we'll go over the answer to this question. All right, welcome back. Well, we're going to try and use this formula for expectation values in order to calculate whether or not, if we play this game, obviously if we play this game just once, we're either going to gain $10 or we're going to lose $1. And because aces are less common, you know, there's only a couple of aces in the deck, we expect most of the time we'll lose $1, but when we win big. And so using this formula for expectation values, the nice thing that we can do is we can calculate what would happen if we played this game many, many, many times. What's the average expected outcome? Is it positive? If it is, this is a game we should play because over time we're going to make money. Or is it negative? In which case, this is a game that we should avoid. And so in order to calculate our expectation value, you'll notice that we need two things. We need to know the probability of the different possible events that are present in our game. And we also need to know what is the function that we're talking about. And so let's go ahead and start making a list of what our different variables are and what are the associated probabilities and outcomes. And so let me start by making us a little table. First of x, so what is kind of our range of possibilities? And with that, we're going to try and think about what is p of x and what is f of x? All right, so one thing that could happen is we could draw an ace. The probability of drawing an ace, well, there are 4 aces in the deck out of a standard 52 card deck, and so our probability of seeing this happen is 4 out of 52. And f of x corresponds in this case to what we're really interested in is how much money are we going to earn over time. And so f of x in this case is going to be our money. So if you like, that is going to be for our ace drawing, we're going to get plus $10. Now, you could, if you wanted to, enumerate all the different card types that could show up, and each of those are going to have the same f of x. And so, really, the only other x that we need to account for is not an ace, because I don't really need to delineate it further. Now, everything but those 4 cards in our 52 card deck is going to be not an ace, and so our probability of drawing a card that's not an ace is 48 out of our 52 options. And in any of those cases, we're going to lose $1. So that's going to be our value of f of x. And let me make an important note here, is that you may notice that the sum, so we'll put notice because this will be important for us. Notice the sum of all of our probabilities adds up to 1. And this is not a coincidence. It turns out whenever we're using these formulas, we have to be in a situation where all of the different options that could possibly occur are accounted for. Otherwise, our formulas aren't going to work. We're not really going to have something that represents probability. And so this key condition of having all the sum of our probabilities add up to 1 is called normalization. And whenever we're working with functions or situations that are described by probability, anything that is physically realistic should be a case where all of the probabilities add up to 1, right? If we're talking about whether or not it's going to rain, if there's a 50% chance that it's going to rain, there has to be a 50% chance that it's not going to rain. If we're talking about getting scores or grades in a class, if there's a 30% chance that you get an A in the class, there has to be a 70% chance that you don't get an A in a class. And so normalization is going to be really important once we start talking about quantum chemistry. For this example, it sort of just happened, and it's maybe a good check for us that we should make sure that we add up, if our probabilities add up to 1, because otherwise we probably forgot about one of the possible outcomes in a particular situation. Okay, and so now that we have our table filled out of what are the possible outcomes, what are the associated probabilities, and what is the quantity of interest associated with each of those outcomes, in this case, how much money do we make, we're ready to calculate our expectation value. And so to go ahead and do that, we're going to say that our expected amount of money that we're going to make, maybe I will call this function our money that we're making. So our expected money is equal to sum over x, just like in our formula above, the probability times the amount of money that we make for a particular outcome. And so in that case, that means that we need to add up our 4 out of 52 chance of getting an ace and making a lot of money, plus our much more likely situation of not getting an ace and therefore losing some money. And if we go ahead and calculate the value of this, you'll see once you plug this into your calculator that on average, we're losing about 15 cents. And so let me put this in context. This 15 cents means that this is the average amount that we make per round of this game. And so if we play the game once, obviously we either make $10 or we lose $1. But if you were to play this game 100 times, that would mean that on average, we would expect to lose 15 cents per time we play this game. And that means that out of your 100 games times 0.15 cents means that you're going to expect to lose about 15 bucks if you play this game many, many times. And so our net conclusion from this exercise should be that this game is a bad idea. And I would say that this is actually something that gets used all the time in practical life because casinos set expectation values for their game to always be just slightly negative so that you as the user are never incentivized to play a game, but that a lot of times you can get tricked into it because if you just read the text of this game, you know, winning $10 versus only losing $1 does sound like you're going to make it rich in the end. And so expectation values are a really good way for us to calculate what's going to happen in a situation when we take the long picture, when we take the long view. Okay, so with that, let's move on to a second example that is going to sound like a really very similar game, but it's going to introduce a few mathematical tricks that change a little bit when we start talking about continuous variables versus discrete variables. So here's our second game. We've got another shady man, still in a trench coat, and he offers to play a different game with us. And it's gonna cost us, so we have like sort of an ante to this game. Every time we play each round, it's gonna cost us $30. And we can play as many rounds as we like once again so that we can take this like average view or this long expectation value. And here's how the game works. The man is gonna use a random number generator, and once again, we'll assure you that he's honest, so it's actually a random number. And he's going to come up with a number between 0 and 10, decimals included. So the number could be 6.732, the number could be 1.899999 repeating. Whatever the number is, you're going to earn back that much money squared. So if he rolls a 3, you're going to earn $9. But remember, you had to pay $30 to enter into this round of the game, so you have a net loss of negative $21. If your number is 6.72, you'll earn $45, and that gives you a net profit of a little more than $15. And so it's going to be the same question as before. Thinking mathematically in terms of whether or not we want to play this game many, many times, should we play this game? Why or why not? All right, so two things that we got to worry about here. One, again, is going to be the fact that we'll need to set up a little table of what are our possible values, what is the probability associated with each of those values, and what is the quantity of interest at each of those different instances that could show up. But the second thing that we may already start to worry about is notice that if I wanted to make a table of this, it would be an infinitely long table because I'm not dealing with discrete variables. It's not just the numbers 1 through 10, it's the range of all possible numbers between 0 and 10. And so the difference between this example and the first example is that here we're dealing with a continuous distribution. And why that's important is that our formulas that worked so nicely for us in the discrete case have to be modified slightly in order to work for the continuous case. And so we had two formulas so far that we talked about in this lecture. One of those, and the one that we're going to focus on, I think you'll be able to see how the expectation of value of x changes, is that we had f of x is equal to, remember, that sum over all possible values, and we're going to multiply together for each value x, the probability and the value of the function itself. Put this over here. And so this is what our formula was when x was a discrete variable. If you remember from your calculus class, whenever we start talking about a continuous variable, an integral by definition is the sum over very small increments. And so if we want to talk about continuous variables, we really just need to replace this summation with an integral. And so how we're going to modify this is f of x is now going to be equal to an integral over all possible values x. And we're still going to have the same formula, but I need to introduce my little integrand, d of x, and then you'll also notice that whereas in the discrete case I used a capital letter p, in the continuous case I'm going to use a lowercase p, and to be very precise with my language, you'll see this referred to in textbooks as a probability density rather than as a probability itself. And so these probability densities work almost identical to how it works in the discrete case. We just need to be able to use our probability density, and it's p of x times d of x that we'll employ. Okay, and so just like before, we need to figure out what is our function of interest and what are the probabilities in order to solve this question. And so let's start off first by thinking about what is it that we're trying to calculate. What I'm really interested in is round to round, what's the average amount of money that I stand to lose or make in this game? And so just like before, I'm going to call this with capital M for the money that we make. You could have chosen a different letter and it would be perfectly fine. And that, by our formula definition, is going to be, we need to find out what this probability density is. And we need, in this case, to calculate what is the amount of money that we're going to make for a given value of x. And then don't forget about our d of x. Now, the amount of money that we stand to make, we can get just by looking at the problem statement a little bit more. So I am told that whatever value gets rolled, and so x in this case is really the range of possible values that could be rolled when I give this shady man my $30 and he uses his random number generator to get a number 0 through 10. So the amount of money that I'm going to make is whatever he rolled squared, but then I'm going to subtract off $30, remember, because I had to pay some amount. And so if I, based on my roll, get $30, well, that's really a net profit of 0. And so that's why I'm going to subtract off 30 in this case. What about my probability density? This one's a little bit more tricky because I'm not explicitly told what the probabilities are. The only thing that I know is that the probability density is constant, right? There's nothing in the problem statement, and in fact, I tried to encourage us to say that it's truly random, so there's an equal probability of getting rolling a 1 versus rolling a 9 versus rolling an 8. And so, but that doesn't actually tell us what the probability density is. And this is going to be the first instance in which our normalization condition is going to help us take something that we know about the probability density qualitatively and then turn it into actually numerically knowing what the probability density is. And if you remember, that normalization condition is the fact that if I sum up over all possible value x, or in this case, if I integrate over all possible value x, then the sum of those probabilities had better add up to 1. And so we're now going to set up actually an equation where we can solve for the probability density. So for now, I'm going to say that the probability density, we don't know what number it is, but we do know that it should be constant because we have sort of a uniform distribution of our probabilities. So let's go ahead and say that this probability density is equal to c, some constant. And then based on normalization, we can solve for what c should be. All right, so we know that our sum of probabilities over all x should add up to 1. And that means that my integral over all values of x in this case means 0 to 10 because that's what the problem's told me. And we have our number c here. We know this should add up to 1. All right. Remembering back from our calculus class, the integral of a constant is that same constant times x. And so that means that c, we've got x times c from 0 to 10 had better equal 1. And substituting in our integration values, let me move all of this over. Substituting in all of our integration values, that means that we've got an upper bound of 10, a lower bound of 0, times c is equal to 1, and that in turn means that c is equal to 1/10. And that kind of makes sense, right? Like there's 1/10 of a shot that we're somewhere around this range. And why this is a probability density and not actually a probability is that each, like within that range of 10, each like individual sliver as we go decimal point to decimal point, that's where that dx is going to come in and tell us what our actual probability is. So p of x is equal to c, which now we know that is equal to 1/10. Okay, so we know what our function is that we're interested in. We know what our probability density is, and so now we can go ahead and solve for the expectation value of how much money we stand to make or lose in this situation. So again, I would pause the video at this point and see if you can follow along and work out the algebra for this problem before I go ahead and do it. Okay, so we've got m of x is equal to an integral. Again, it's important to know, we have to know what our integration bounds are. In this case, it's between 0 and 10. And we've got our probability density is 1/10. And then our money-making function is x squared minus 30. Don't forget our dx. And now we just need to integrate and solve. So I'm going to go ahead and pull out this factor of 1/10 out of my equation. And my integral of x squared is going to be 1 over 3 x cubed. And then minus 30, the integral of that is minus 30x. And I'm going to integrate this I'm going to plug in my two bounds, my upper and my lower bound of 0 and 10. If I do that, that's going to give me 1/10 times 1/3 of 10 cubed minus 30 times 10. The fact that our lower bound is 0 is kind of nice for us. And so then the last thing that we need to do is just plug this into our calculator and solve for the numerical answer. So we've got 1/3 times 10 to the third minus 30 times 10. And then all of that we want to divide by 10. And so that gives us a net result of plus $3 in a little bit. And so our answer to this question, it turns out, is yes. Assuming we can play this game many, many times, we stand to gain on average about $3 every time we play this game. And obviously there's going to be a lot of variance. One round we might get, we might lose $30 because we roll a 0 and we already paid $30 for the game. Another round we might roll a 10, we get $100, and even with our entry fee of $30, that's still a net profit for us of $70. And so this game is advantageous for us. But one thing we might be curious about, I am not a person, for instance, who likes a huge amount of risk. And so we might want to ask ourselves the question, how much variability should we expect to round? Should I be worried if on one round I gain $70 and another round I lose $70 or $30? And so we're going to spend our last little bit of today's lecture talking about how we think about variability when it comes to these formulas around expectation values. And so I'm going to start by just giving us the formula for standard deviation, not as you've seen it before in your algebra course or in general chemistry, but instead using this languages of expectation values. And so in that case, our formula for the standard deviation which we'll still use our Greek letter sigma to denote this. This can be given by calculating the expectation value of our quantity squared minus, and I should actually make this an f of x. So we've got our expectation value of f of x squared minus our expectation value of the quantity squared. And so one thing we might immediately note about this or want to figure out is, well, this formula would be really easy if we could just guarantee that the two quantities I talked about, so the function squared, its expectation value, versus the expectation value of the function squared. Are those two things the same? And it turns out they're not. And so I'm going to write this down as another important note, because this is something that folks will forget about all the time and try and set these things equal. These two quantities are not equal to each other, generally speaking. And if you wanted to see that, one way we could look at it is to plug in our previous formula for how this looks. So remember that the expectation value of f of x squared would be given by my probability density times this function squared, d of x, versus my expectation value of the function would be me taking my probability times f of x dx, figuring out whatever that is, and then squaring that. And so hopefully you can see why it's the case that when we do our standard deviations, having the squared inside of the expectation value versus on the outside is a big deal mathematically. It means that this function is going to be really different. Okay, and so let's go ahead and use this formula now to calculate our expectation value or our standard deviation, and then we'll go ahead and wrap up for today. All right, so in order to calculate our standard deviation, we've already calculated the expectation value of f of x, or in our case, m of x, since that's what I decided to call our formula. So the only thing that we need to do is calculate the expectation value of m of x squared. And so let's go ahead and do that. So if we remember from an earlier line, we defined m of x as x squared minus 30. And so in order to calculate this expectation value, we're going to do our integral, still between 0 and 10, of our probabilities times, in this case, m of x squared dx. And so substituting in what we know, so each of the probability densities, our probability density is 1/10, it's just a constant, and m of x is x squared minus 30 squared dx. And so going ahead and doing the algebra / the calculus to solve for this, that means that we have our integral. I'm going to go ahead and pull out this factor of 1/10. And we've got, when I square this quantity, I'm going to end up with x to the 4th minus 2 times 30 times x squared. So we have two factors of that negative 30x squared, and then plus 90. in this case, dx. And now, using our basic rules of calculus for how to do integrals, we're going to get that x to the fourth integrates to 1/5 x to the fifth, minus 60x squared is going to integrate up to negative 20 x to the third, and then plus 90 turns into plus 90x. And we want to evaluate this over our limits of integration, 0 to 10. All right, and then now that we've done this, we just need to plug in our values and solve for that numerically. And so let me go ahead and do that on my calculator real quick. So we've got 1/10 times 1/5 times 10 to the fifth minus 20 times 10 to the third plus 90 times 10. And when we put all of that together, it looks like we get a value of 90 out. Let me make sure that Yep, all right. And so our standard deviation then becomes $90 minus our expectation value squared. So we've got 90 minus $3 squared, and then take the square root of that in order to get the standard deviation rather than the variance. And so 90 minus 3.33 squared is going to give us an expectation value, or sorry, a standard deviation of $8.88. And so what we can learn from this in terms of our whether or not we want to play this game is I had better have, on average, about $10 of ready cash, because even though I expect to gain $3 per time, it's not unusual for me in a particular round of this game to gain $11, and it's not unusual for me in a particular round of this game to lose $5. And so just like you would do in your chemistry class, if we wanted to talk about kind of what's the range of probable values for our expectation, we often report that as an average or an expectation value plus or minus the standard deviation. And so we might say that our game expectations is to earn a little over $3, but plus or minus a pretty large variance. Okay, so that is all that I wanted to share with us for today. And so to summarize our takeaway messages from this lecture, we learned a little bit of new terminology. So instead of calling things averages, now we can expect to call things expectation values. That was an unintentional pun. And those angle brackets is what denotes the fact that we're talking about an expectation value. You're going to start getting used to seeing capital P of x or lowercase p of x, depending on whether we're talking about discrete variables or continuous variables, but it's going to be really important for us to know the probability of a certain event happening. And then there's a couple of formulas that we learned today. And so our formulas to know is 1, the expectation value for a particular variable or a particular function that's of interest. And that means that we just need to either add up or integrate the probability times the function of interest at every point. And then a second important formula, or maybe just lesson that we learned, is that for all realistic systems, probabilities have to be normalized. And that means that either the sum for discrete variables or the integral for continuous variables over all possible values x has to add up to 1. And then last but not least, we learned a formula for how to calculate the standard deviation of a distribution, and that is given by calculating the expectation value, or the average of the quantity of interest squared, minus the expectation value of the quantity of interest squared. And in general, we also learned, and we should keep in mind, that those two quantities, whether or not we have the squared inside or outside of those angle brackets, really does matter, and that those values are in general not the same. Okay, so that's all for today. I look forward to seeing you all in class so that we can do some practice problems with these concepts that we've just learned. Until then, see ya.